This is Science Max, Experiments at Large. Science Max! On this episode of Science Max, I'm on a quest to harness the power of lightning. Its balloon-sticking, hoop-levitating, hair-raising power is all thanks to static electricity. Hold on to your grounding rods. There's electricity in the air. All on this episode of Science Max, Experiments at Large. Greetings, Science Maximites. Welcome to Science Max, Experiments at Large. My name is Phil, and today on Science Max, we're going to be harnessing the awesome power of lightning. How are we harnessing the power of lightning, you ask? With this balloon. I know what you're thinking. You're thinking, Phil, what's similar between a balloon and lightning? Well, nothing right now. But behold, as I use the power of static electricity and rub the balloon on my head. Because basically that's how it starts. You see, when I rub this balloon on my head, it's stealing electrons from me, creating a positive charge in my hair and a negative charge in the balloon. And the interesting thing is, you know that things with opposite charges attract each other, right? Something that has a positive charge will attract negative things and vice versa. But anything with a charge will attract anything with a neutral charge. See all these things on the table? They all have a neutral charge, which means they've got equal amounts of positive and negative. Right now, this balloon is building up a big negative charge, which means it will be attracted to all of these things. This can of Science Max soda, it has a neutral charge. The balloon has a negative charge, which means the can will be attracted to the balloon. And this paper is neutrally charged, which means the paper will be attracted to the balloon. And if you hold the negatively charged balloon next to neutrally charged sugar, haha, sugar storm. And you probably, wait, I don't want to get sugar in my hair. And you probably know this trick. If you rub a balloon on your head, you can stick it on the wall. Ha-ha! But what does any of this have to do with lightning? Well, the same thing is going on with a lightning bolt. The clouds become negatively charged, and that negative charge wants to equalize itself with the ground, which is neutrally charged. And that lightning bolt is the electricity jumping from one place to another. And you can see this yourself. If you rub a balloon on your head and you put it next to something metal, like a doorknob, there'll be a spark. But here's another thing you can do if you don't have a balloon, which I guess I don't anymore. Rub your feet, if you're wearing socks, on a carpet, and then turn out all the lights and touch a doorknob. You might be able to see a spark jump from your finger to the door. That's lightning in a very, very small form. So that's what we want to do today on Science Max Experiments at Large. Max out lightning! I think I'm going to go to the Ontario Science Centre and ask Heather her advice. She really knows her stuff. I'm going to go see if she's busy right now. Come on.
You got the portal fixed, though.
Well, it's not exactly fixed. It's still got a couple bugs that I'm ironing out, but I stopped coming in 10 feet above the floor.
Hey.
So that's a step in the right direction. Anyway, Heather, I've come here because I want to ask your advice on something.
Yeah, for sure.
Awesome. So what I am doing is creating lightning. So this is where I'm at right now. So this is a balloon. I blow up the balloon, and then I rub it on my head, and it creates a static charge, right?
Yeah.
Just like in the lightning bolt between the clouds and the ground.
And the ground.
So I was wondering if you could help me maybe max that out, and I thought the perfect place to start would be a larger balloon.
Ooh, right on. Actually, yeah, I like this.
Yeah.
I've got a big balloon, if you just give me a second.
Sure.
All right, catch.
Okay. All right, giant balloon. So what I figured is I'll just start rubbing it on my head.
Okay.
And then we could maybe stick it to the wall or something?
Yeah, I think instead of a wall, we can even try on this whiteboard here.
Oh, okay, great.
Keep rubbing.
I'm rubbing. Okay, ready?
Yeah.
Here we go.
And
So that That didn't exactly
Right?
work.
Yeah.
Both of us rubbing our heads on the balloon.
Okay.
And go. Wow, that was a whole lot of nothing.
Well, we've got a really heavy balloon here.
And I
so-
feel like our heads are only this big, so we can't cover as much surface area of the balloon.
Fortunately, you can also build up a static charge by rubbing a balloon on a sweater. Or if your balloon is giant, rubbing sweaters on your balloon. But even that didn't work so well.
I think what we need to do is come up with a better way to create a difference of charge.
Yeah. Let's forget about the balloon.
You have something else?
I have something else really awesome here at the Science Center. You want to check it out?
Yeah, absolutely.
Yeah, right.
Should we take the sweater and the balloons, or should we leave them here?
We'll leave them here.
Okay.
So here's how static electricity works. Normally, everything has equal numbers of positive and negative charges. That's when things are said to have a neutral charge. But when you rub a balloon on your head, the balloon develops more negative charge than positive because it pulls electrons from your hair. The same thing happens in clouds during a storm. The cloud develops a negative charge when water molecules start bumping into each other. A lightning bolt happens when the negative charge in the cloud gets so big, the attraction to the positive charge in the ground gets strong enough that the electrons can make the jump all the way from the cloud to the ground, and you get lightning. Heather and I tried to max out the static on a balloon, but a big heavy balloon just doesn't hold the same charge.
That didn't exactly work.
Yeah.
But we're only interested in maxing out the static charge, and Heather knows just what to use.
Wow. So this is the Ontario Science Center
Yes.
electricity show.
Yes.
Okay, so where's the electricity part?
The one we're going to be playing with is right there.
So the giant mushroom.
Yeah, well, it does look like a mushroom.
We're gonna make some sort of electricity salad.
All right, head on up onto that platform right
Oh, okay.
there. And I need you to put one hand on that silver ball, yes. So the way it
Nothing
works...
is happening.
Patience.
Okay.
Once I turn it on, when I engage it, this is going to steal your negative charge. So it's going to steal your electrons. So if it steals electrons, you're going to be positively charged.
So it'll make me more positive.
Even more positive.
Yay! Woohoo! I am positive.
Here we go.
Woo!
This machine is called a Van de Graaff generator, and it pulls the negative charge away from the person touching it.
That is great.
Instead of having equal amounts of positive and negative charges, you become positively charged.
Woohoo! Science hair! Yeah!
Like when you try to put two positive ends of magnets next to each other, each hair on your head starts to repel the others and be repelled from your head.
Science hair! Dude!
So your hair stands up.
Ah, yes! Woohoo! I can't see anything. So this is more of a machine to generate hair standing up, but it doesn't make lightning.
Oh, well, actually, I have a demonstration in my back pocket. This is going to help us
Okay.
to create lightning. This is our grounding rod.
It is my scepter of science.
And so we're going to use this to continuously provide that negative charge.
That's
to
why it's
static.
plugged in.
That's why it's plugged into the ground, yeah.
Okay.
Okay, so then if you touch it to that metal ball, got it? Not too exciting, right? So pull away and let's see what happens.
Whoa! This is what I'm talking about.
Very good.
The Van de Graaff creates a positive charge. The rod has a neutral charge. When the difference becomes big enough, the charge jumps the gap.
Behold, I have the power of lightning! So it's the difference between the positive and the negative is what we want when we want to make a lightning bolt.
Yes.
So is there something we can use to make that happen? Large difference of charge?
Yeah, I think I have just the thing.
Oh, yeah?
Yeah, you want to check it out?
Absolutely.
All right,
Okay, let's
do
go.
it.
So, you would like to move electricity from here to there. Well, what you need, my friend, is a conductor. All right, a little more arpeggio this time. No, not that kind of conductor. All aboard? No, not that kind of conductor either. This kind of conductor. I know what you're thinking. You're thinking, hey, that's just a piece of metal. Well, that's right. That's because you're smart. This is a circuit. Electricity flows from this battery along the wires and into the light bulb. But Sal, you cleverly observe, the light bulb is not lit. This is true. That is because we have a gap in the circuit. And air is not a good conductor of electricity. Is metal a good conductor of electricity? Let us find out. Wahaha! Metal is a good conductor of electricity. What about wood? Nope. What about this horseshoe? Is a good conductor. Will this sandwich conduct electricity? Nope. No. What about this plastic fish? Nope. What about this pickle? No, pickle is not a good conductor. That's why we make electrical wires out of copper and not pickles. You know, in case you were wondering.
Lightning bolts make interesting patterns. That's because the electricity is searching for a way to get from one side to the other. But it's hard to see the patterns of lightning bolts because they happen so fast. Fortunately, using the power of science, we can observe these patterns for ourselves in a motion we can perceive. I'm going to use electricity to recreate a lightning bolt pattern. I've got 2 nails in a piece of wood here, and I'm going to attach electrical leads to both nails. Now, the electricity wants to go from that side to that side, but it can't. It has to go through the wood, and wood is not a very good conductor of electricity. Now, this is very dangerous. I need a special machine even to pull this off, so this is definitely not something you want to try at home. In fact, I'm gonna stand way back here when I turn it on.
Like water, electricity tries to find the easiest route to get from one place to another. But sometimes that involves branching out until the right connection is made. Lightning bolts do the same thing when they branch out between the clouds and the ground. Finally, there's a spot where the branches meet and the circuit completes itself. Then the electricity follows this one path, ignoring all the others.
And there you go. We just watched a lightning bolt happen in slow motion. Haha, science.
Back to our main experiment where Heather and I are on a quest to use static electricity to recreate a lightning bolt. Our experiments with the Van de Graaff generator had some hair-raising results, but Heather has another experiment she wants to show me.
This is Jacob's ladder.
Oh, so this is another way to make lightning.
Yes.
Lightning?
We're gonna see, yes.
Let's do it.
All right.
How do we get it to go?
All right, so we want to turn it on.
Behold! Oh, turn it on,
Not-
okay.
not-
Go!
Oh.
Ooh, look at that!
You can actually see that light climbing up between the 2 copper wires.
That's why you call it Jacob's ladder, because it's got the rungs of the ladder.
Yeah. Between these 2 points, there's a really great charge difference, right?
Okay, so what's the difference?
10,000 volts if you're looking at it.
10,000 volts. And
Yeah.
volts is how you measure the difference in charge.
Exactly.
Why does it go up?
So it goes up because rather than just staying at the closest point, is because we're heating up the air.
Oh,
certain point,
so
yeah.
hot air rises.
Hot air rises.
And it takes the electricity with it? So if we cooled the air, it wouldn't go up?
Wouldn't immediately go up, yeah.
And there it goes, and it heats back up again.
Yeah.
That's neat. Okay, so we have a Van de Graaff generator. We got a Jacob's ladder. Are there any other devices that make lightning like this?
Ooh, yeah, there's other things like the Tesla coil, really high.
I have a Tesla coil.
You have a Tesla coil?
I do. I've got one at the lab. I've just never known how to hook it up.
Oh, I can help with that. Yeah.
Really?
Yeah.
Okay, let's do it. Let's go back to the lab.
All right. Well,
should-
yeah.
I'll turn that off. Okay.
Yeah, safety first.
Okay. By now, you're probably an expert on what happens when you rub a balloon on your head, right? The balloon becomes negatively charged, which means it will attract anything of an opposite charge, or anything positive, or anything that is neutrally charged, like, well, like me. Look at the hairs on my arm when I bring the balloon close. Whoa! You see, the neutral charge in my body is being attracted to the negative charge in the balloon. So if something is negatively charged, what happens if you bring something else negatively charged nearby? Well, they'll repel each other. And here's an experiment you can do to make something fly using static electricity.
You'll need a balloon, a sweater, scissors, and a plastic bag out of the thinnest plastic you can find. Fold the bag up and cut off the bottom. You don't want that part. Then cut another strip from the bag. This will give you a hoop of plastic. I find it works better if you break it and tie it again. Lie it flat and rub it with the sweater. This will give it a negative charge. You'll know you've got enough of a charge when it really wants to stick to the table.
Then take your balloon and rub the sweater on the balloon to charge it up.
Because both the balloon and the hoop have negative charges, they repel each other.
Then put them together and it will repel.
And you can get the hoop to levitate.
Ha-ha, a floating bag of static charge. But here's the thing, you need to keep it away from your body, because if you get close, the bag will stick to you, because you're neutrally charged and the bag is negatively charged. Pretty cool, right? Well, let's max it out. Maxed out floating static ring. Whoa, no. Yeah! Look out, look out! Oh, no! Oh, sorry about that. Oh well. It was fun while it lasted. I gotta charge these up again.
Being a chef is my absolute passion. And cooking up science recipes is my speciality. I'm Buster Beaker, and this is Cooking with Science.
Oh, hello. I didn't see you there. My name is Buster Beaker, and welcome to Cooking with Science. Let's say, for example, I've spilled the salt. Oh no, look at me. I've spilled the salt. Oh, there's salt all over the place. Not really a big deal, right? All you have to do is clean up the salt, put it back in the container. But oh no, I've also spilled pepper on the salt. But that's all right. You might be able to carefully separate the set. But no! Oh dear, look, the pepper and the salt are all mixed together. What do? Well, here's how you can save the day using the power of science. All you need is a cloth and a plastic spoon. Like this one here. Just rub the plastic spoon on a cloth, and you'll be charging it up with a negative charge of static electricity. If it's got a negative charge, it will attract anything that has a neutral charge, just like the salt and pepper. But I know what you're thinking. How will we separate them? Well, here's the answer, my friends. Pepper is lighter than salt. Observe. So if you hold the spoon high enough, the pepper will be attracted and make the jump up to the bottom of the spoon, but not the salt, as long as you've got it high enough up. Because the salt is heavier, you'd have to bring the spoon closer, which we're not going to do. And if you tap it off to the side, you'll make a nice little pile of pepper, and there you go, separating pepper from salt using the power of science. Thanks for watching Cooking with Science. I'm Buster Beaker.
Heather and I have been on a quest to recreate lightning using static electricity. We've gone from balloons to a Van de Graaff to a Jacob's ladder, each more lightning-y than the last. Finally, Heather suggests we use a
Tesla coil.
Oh, is this named after Nikola Tesla?
Yeah, he invented it.
Oh, one of the founding fathers of electricity, right? I love
on.
Nikola Tesla. He's cool. So how does it work?
So the way this works is it is a step-up transformer, meaning we take a lower voltage and bring it up and ramp it up to a much higher voltage.
Okay, so normal voltage is 120 volts. That's what we have a normal plug-in
Typically,
socket.
we're getting it out of, yeah, exactly. And we're gonna ramp that up to really high amounts, upwards of 25,000, maybe even 250,000.
Wow.
Volts.
That's a lot.
And all that charge buildup, we're gonna see something pretty amazing happen.
Okay.
Do you wanna see it?
Yes, we stand back there, right?
Let's check it out. And
The Tesla coil builds up a charge which jumps through the air to this neutral rod, just like a lightning bolt.
We made a lightning bolt! That totally jumped a long way. That was impressive.
that was a really good one.
So can you control it?
Yeah.
Okay, show me.
You wanna see?
All right.
I'm going to lower my frequency.
Okay.
Let's see what happens.
Oh, that's amazing. Oh, it's like a scattered lightning bolt. Oh, wait a minute, so you can play different notes?
Play different notes.
I need 5 minutes, hold on.
Okay.
Okay. All I need is 5 minutes. You know, I was thinking is if you can make different, hold that for a second. If you can make different frequencies, that means you can make different notes, right?
Right.
So I don't need that either, hold on. That's not what I need. Okay, one more thing, can I get that hammer? Okay. Yeah, okay, ready to go.
So what is this?
When you told me the Tesla coil could play different frequencies, I thought we could make different notes come out of the Tesla coil, so I programmed it to play the notes of the Science Max theme song.
What?
Yeah! You wanna hear?
Yeah.
Let's try it. Yeah! Science Max, experiments at large, lightning bolts!
Speed lightning!
We have created lightning! Woohoo! Lightning dance! Science Max! This episode of Science Max is all about generating electricity. Where do we get this electricity that we use all the time? We try to generate as much as we can using human power, plus solar energy, tidal energy, wind energy, and more. All you need to do is
Turn the generator.
all on this episode of Science Max Experiments at Large.
Greetings, Science Maximites. Take a moment and imagine with me, if you will, a time when the only way to light your house was with candles or oil lamps. There was no electricity. That meant no power tools, no video games, no telephones, and worst of all, no TV. Fortunately, we live in a world of electricity. If you've ever lost power in your city or neighborhood, you know how hard it is to get by without electricity, even for one day. But where does it all come from? Where do we get this electricity that we use all the time? We make it. That's the cool thing. And I can show you how to make it as well. Check it out. All you need is an electric motor. Electric motors are pretty simple. All you do is get a battery and you attach it to the electric motor, and that makes it work. There we go. Attached to the battery, it spins. But if you spin the electric motor, it creates electricity. And that's what we're gonna look at today, creating electricity. We're gonna build a wind turbine. But first, you need an electric motor. And you can probably get one from a broken toy. Just make sure that the toy is broken and that the broken part isn't the electric motor.
Here's what you need: index cards or construction paper, scissors, push pins, science tape,
It's the same as invisible tape, except I use this one for science.
a cork, chopsticks, craft sticks, and modeling clay. And remember, all the steps for this experiment are on our website. To begin, cut the index cards into strips and tape down a push pin so it sticks out. Then fold over the index card and tape it together. Then stick the pin into the cork and repeat that step.
If you want as many blades as you can get on your fan, you're welcome to do that.
Next, take your modeling clay and stick the chopsticks in, then tape the craft sticks in between with science tape. Then take the motor and stick the cork on the end, then wedge the motor in between the craft sticks and tape it down so it stays put.
And there you go, a fan that will spin in the wind.
You want to adjust the fan blades so they all face on a bit of an angle. That way they will catch the wind and spin.
There we go. Now when it spins, it will create electricity. I'll show you with this. It's a multimeter. And a multimeter measures little amounts of electric current. There. The hairdryer makes wind, spinning the fan blades, and we are creating electricity. Now, pretty much all electricity that you make comes down to turning a generator. A small motor like this isn't gonna produce a lot of electricity, barely enough to power one tiny little LED, but it's a start. And a good start is all we need, because today on Science Max Experiments at Large, we're gonna look at all kinds of different ways of generating electricity. Plus, I wanna find out just how much electricity one human being can generate. Although one human being is gonna be kinda lonely, I'm gonna need an expert. Oh, I know, Anthony from the Ontario Science Center. He can help. I wonder if he's busy. Well, come on. Oh, Anthony!
Phil?
So I was wondering if you could help me with an experiment. I want to generate as much electricity with human power. What do you think?
I think that sounds awesome.
Okay, great. Let's go back to Science Max headquarters.
Is that the portal?
Yeah. Don't worry, all the kinks are worked out. I know what it is. It's this. Where did you end up?
I was in the vents.
Oh, I ended up in the bathroom. All right, well, now that we're here. Okay, so this is what I started with. And this is just, you know, an electric motor, right?
Right.
So you can generate electricity, you spin it, so I figured in order to generate more electricity, you get a bigger generator?
Exactly, yeah. The bigger the generator, the bigger the magnet, the more the copper, the more the electricity.
Oh, well, you know what we should do is we should just get an even bigger one, like a giant one that they use in like at a power plant or something, or?
Not quite. That would be too big for a person to be able to turn. It'd just be impossible.
So you think this is a good size?
I think this is a great size.
Okay, so that's good.
This is called a multimeter. We're gonna hook up the wires. I will do black to black.
Black to black.
To red. And as you turn our generator, we can see just how much electricity we're generating. Okay, so.
Here, you hold on to that.
This,
and
you
I'll
can
turn
start
the
turning it.
generator.
Now it's time to play How Much Electricity Did They Make?
2.4 volts, yeah, it's not bad.
Oh, 2.4, yeah, it's not great.
That's just enough to power a small LED flashlight. Better keep trying, boys.
I got some handles here that we're going to attach
that
to
would be
the
perfect.
end of the generator so
Yeah.
we can spin it.
Okay, let's try.
No matter how fast I cranked the large handle, I couldn't make any more electricity than before.
Okay, let's try something else.
But it's a smaller handle.
Perfect, okay, yeah.
That's good?
Yeah, well, maybe it'll let us get more spins in.
Oh, yeah, because I don't have to make as big a circle.
Exactly. Yeah, it's working already. We're up to like 3.5,
Now, how much electricity is Phil making?
4.5.
That's the same as 3 AA batteries. Maybe enough to power a toy car. Still, a long way to go.
Yeah, it's a lot higher with the faster spins. Oh, all right. You okay?
I'm okay.
Maybe we could use like some gears or something like that.
Oh, yes, you know, that's a good idea because this circle that I'm making here, I can only go so fast. So
Yeah.
maybe with gears, you can do 1 circle here equals like 10 circles on the other gear.
Exactly.
Yeah.
Okay, so kind of like the gears on like a bike.
Yeah, the gears on a bike or something like that. A bike! Of course! Yeah, so, okay, so we get a bike and we attach the back tire to the generator.
The generator, and then you can use the pedals of the big gear to power the small gears.
Okay, great. We'll go get a bike.
Yeah.
Yeah, high five. All right. Oh, right, they're over here. This is a generator. It generates electricity when you spin it. But how does it work? What wizardry is inside? Well, actually, generating an electric current is fairly simple. All you need is 2 things. First, you need a conductor, like this coil of copper wire, and you need a magnet. Now, this is a galvanometer. It measures small amounts of electric current, and I have my copper wire attached to it. Watch as I put the magnet inside the copper. I get a little bit of an electric current, and then I take it out, it goes in the other direction. A little bit going this way, and then I take it out, a little bit going that way. Positive, negative, positive, negative. This kind of current that goes back and forth is called alternating current, or AC. It's the same kind of electricity you have in your house. But here's the cool thing. Watch this. I put the magnet in and I leave it. It goes back to 0. You only get electricity when you move the magnet. All right, so let's create our generator. Instead of starting with a copper coil like this, what if we just had the magnet and we have it staying still, like that, and we move the conductor past it, like spinning? It's good, but not great, because we're only getting a little bit of electricity as it passes. So let's make it more efficient. Let's put in some more magnets, 1 on either side, and one on the top. And now when we spin it, it goes past all of these magnets, and every time we get a little bit of electric current. Well, this is how a generator works. If you take an electric motor or a generator apart, you can see there's a coil of copper wires on the shaft, and it spins around like this. And on the inside, there are magnets. So there you go. When you put it together and spin it, you get an electric current. Or if you put an electric current in it, it will spin, just like an electric motor. And that is how a generator works.
Anthony and I are trying to create as much electricity as we can using just human power. But so far, it hasn't been going so well. It all comes down to how fast we can spin the generator.
Maybe we could use like some gears or something like that.
In order to get it spinning really fast, we're gonna use a bike. It's just a matter of getting a bike, taking off the wheel, putting it on a stand,
It is now a stationary bike. It'll be even more stationary once we screw it down.
and attaching the generator.
All right, the bike generator. Bike-orator, what should we call this thing?
Bike-nator.
Bike-nomator. I like it. So, okay, let's go over what we've got here.
Okay, so we've got 2 gears. We've got a big one, we got a small one. We turn our pedals, and the big gear turns the small one.
So this is the whole point of this build, is so that we can get one revolution here means a whole bunch is spinning there.
Exactly. The more we get here, the more our generator spins, and the more electricity we get. We get tons.
Awesome. And obviously using bike, because you're using your legs.
The strongest muscles in your body.
Awesome. Okay, so now what's with this horn? That is a loud horn.
I know. I tried to warn you.
That is great. I love that.
So Anthony and I hop on and give it a pedal. We pedal as hard as we can, and we produce a pretty good amount of electricity. How much electricity did they produce?
We got up to maybe like 18 there. You did a pretty good job.
That's enough for a power tool, like a drill.
It's good. You know what? This works well, I think, for keeping a good number for a long period of time.
Yeah.
So we can get up to like 18, 20, but it doesn't, we can't really get any higher than that.
Yeah, you know what we need is like one really hard pull, like all of a sudden. That way you can get like a spike.
Yeah, you're right. So it's like instead of putting all that effort into it going for a long time, you put all the effort into one quick motion.
Exactly.
Yeah, good idea. So you wrap a rope around here and then you just pull it.
Exactly.
And that'd be a really fast motion. Spin it really quick and get a very high number.
High spike, exactly.
Okay. You know, we're gonna have to take the bike apart though.
Okay,
All right. Well, it's science.
Okay, cool. So I'll just get.
Oh, you know what? We actually don't have to take the whole bike apart. We just have to take the generator off.
Oh, right. Okay.
Okay,
Hang
cool.
on a sec. I got it.
And maybe we should attach the horn to the next thing too.
What do you know?
Turn it off!
It's so loud.
So you want to generate some electricity, but what do you choose to generate that electricity? Hydro, nuclear, coal, solar? Who knows? I do. I know. And soon, so will you. In order to generate electricity, you need to turn the generator. Turn the generator. One of the most common ways to turn the generator is to use one of these. It's a steam engine. Usually they're a lot bigger. You see, you heat the water to boil it and turn it to steam, which works a piston, which turns the generator. Huh? Pretty amazing, right? But what it really boils down to is heating water to make steam. Boil water to make steam to turn the generator. Coal power. Burn the coal to boil water to make steam to turn the generator. Natural gas. That's different, right? Nope. Burn the gas to boil water to make steam to turn the generator. Nuclear power. That's different, right? Nope. It creates heat, which you use to boil water to make steam to turn the generator. Wind power. We don't even need heat for that. Just use the wind to spin the fan to turn the generator. Hydropower. Just pour water across something that spins to turn the generator. No matter what, making electricity always comes down to turning the generator. It's always yada yada, yada yada, turn the generator. Except for solar. Solar does not work like that. But other than that, it's always yada yada, yada yada to turn the generator. And now you know your electricity generation. Hey, Ramona, you wanna come and give me a hand over here? My arm is getting tired.
Whew, it is hot out here. Oh, in order to generate electricity, you need to spin a generator. Most forms of electricity generation work like that, but not solar. Solar panels like this one generate electricity from the sun's energy. So, how do they do it? Well, this is a solar panel. Okay, it's not really a solar panel, I just sort of put this together, but it works the same way. There are two plates, and on these plates are electrons. I've got golf ball electrons up here, ping pong ball electrons down here, but they're all the same thing. Now, this happy little fellow is a photon, energy from the sun in handy-dandy particle form. What happens is photons come from the sun and hit the top plate and knock some electrons from one side to the other, like this. And that knocks over some electrons. Now, these extra electrons travel up a wire in the form of electricity, and we can use them to do work for us. Then they change to the other charge, go back, and we start the process all over again. That is how solar panels work. But remember, it only works when there's sun and photons.
Anthony and I are trying to generate electricity using human power. Spinning the generator didn't work too well, but we found if we used some gears, like those on a bike, it worked better.
You know what we need is like one really hard pull, like all of a sudden.
Using gears is a great way to get work done. The good news is there are generators with gears already in them. That means if we can turn the spindle once, the gears inside will spin the coil a lot of times. The only downside, turning the spindle gets harder the higher the gear. Anthony and I attach a spindle, and then we wind up the rope, which takes a while.
Okay, so the plan is, it's on a big spool now.
Yeah.
And you just run as fast as you can.
Got it.
And we'll hopefully get as many revolutions as we can, depending on how fast your top speed is.
Okay.
Sounds good?
Sounds good. I can be pretty quick.
Okay, good. All right.
Ready?
On your mark.
Uh-huh.
Get set. Go.
How much electricity did they create? 24 volts.
Actually, not bad.
That's enough to power their own personal scooter. Not too shabby, boys.
We need like a hard pull all at once.
Yeah, from something like really big. So what if we could get like really high, like up there? Could we attach the generator up there? You could jump down from there.
And I would hang on the rope?
Yeah.
Yeah, it's good, but I don't want to jump from up there. Oh, what if we put a pulley up there?
That
and
would
then
work.
the rope goes through the pulley and then back down, and then I jump from somewhere much safer, like just on top of here onto a crash mat or something.
That sounds great.
And that's my full body weight on the rope.
That sounds great.
All right, high fives.
Yeah.
Tidal power in 60 seconds.
By now you know that in order to create electricity, you need to spin a generator. Scientists and engineers are always coming up with lots of new ways to use natural forces of the Earth to spin a generator and create electricity. One of those natural forces is the power of the tides. You see, the water in the oceans doesn't stay still. Every few hours, the water, or the tide, goes out. And then a few hours later, it comes back in. So, if you attach a paddle wheel in the water and attach that to a generator, when the tide goes out, it creates electricity. When the tide comes back in, it creates electricity. That is how you create electricity using the power of the tides. It's water power. In fact, hydroelectricity is also using water power. Do we have time to talk about hydroelect? We don't have time? We don't. Okay, maybe come back.
Hydroelectric power in 20 seconds.
20 seconds? Okay, hydroelectricity comes from water. Hydro means water. So all you have to do is find a place where water pours down from a height. And you can put a generator in there, and ta-da, you're creating electricity with the power of hydro. Ha 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 ha. I did it.
Anthony and I have pulled and pedaled, and now we're going to hang on to the rope and use our whole body weight to spin the generator as fast as possible.
Okay.
Okay.
Crash mat. Let me test it out.
Looks good.
Yep, it's good for crashing. So I go up here. Okay, I go up here.
Climb on up. We'll get you the rope. Got your helmet for safety.
Helmet for safety, crash mat for safety. So we have the rope, and it goes up through that pulley, and then back down to our generator with a spindle on it. And as I fall, the spindle will turn.
Exactly.
And hopefully the speed of me falling and holding and yanking it down as hard as I can will be the biggest spike of electricity yet.
That's right. We'll be measuring it on our multimeter. Here.
Okay.
Okay.
Ready?
You ready?
Yeah.
Here we go. 3, 2, 1.
I jump down and my whole body weight pulls on the line.
Oh, that was awesome. That was like our biggest spike ever. That was amazing.
All right, high fives. Biggest spike ever. Is it enough to power my house?
Nope.
How much electricity did Phil generate? Almost 30 volts. How much does he need to power his house? 120 volts. He's still off by quite a bit.
Well, we've learned something. Nuclear,
Wind,
hydro,
solar,
natural gas.
whole power.
It's all great ways to generate electricity.
Yeah.
And human power,
Not so much.
not as good. But human power is more fun.
Yeah, way more fun.
Yeah, so your turn?
Yes.
Okay.
Give me,
You
give
take
me.
the helmet and I'll take the multimeter.
Okay.
And then we'll go and we'll do it again. Okay. Wait, I gotta wind it up.
Science Max is a show where we take small experiments and do them big. If you want to try these experiments yourself, go to our website for instructions. But not all the experiments on Science Max are the kind you should try at home. This one, yes. This, no. Try this, don't try this. A big yes, a big no. I don't know how you could possibly do this one at home. And remember, if you're ever not sure, ask an adult. Science Max! Electromagnets are magnets you can turn on or off when you want. We build our own electromagnet and see just how powerful we can make it.
It held 100 kilograms.
Plus ferrofluid, wizards, and I tried to get to the North Pole using a compass. Now that I'm here, I realize it's really difficult. All on this episode of Science Max Experiments at Large.
Greetings, Science Maximites. My name is Phil, and welcome to Science Max Experiments at Large. At this very moment, half the lab is being held together with the power of electromagnets. And magnet 1 turning off. Electromagnets are a really cool and powerful way to interact with the world. And when I say power, that's because you need power to make them work or not work. Magnetism is an invisible force that has to do with the magnetic fields created by magnets that lets them attract things that are metal or each other. But electromagnetism is a little different. You see, magnets are magnets all the time. It's because of what they're made out of. Electromagnets are only a magnet when you have an electric current going through them, which means you can turn them on or off. Today, we're gonna be building an electromagnet. Oh, that was the wrong switch. Anyway, like I was saying, today we're gonna be building an electromagnet.
You need a bunch of copper wire, a very large nail, or something metal to become your electromagnet, electrical tape, a battery, an on-off switch, wire strippers or a craft knife, and the help of an adult, and finally, something to magnetize, like these paper clips. And remember, all of the steps for this experiment are on the website. To begin, take the copper wire and start at the top of the nail. Leave a little bit of wire sticking out, then carefully start to wrap the wire around the nail. Don't go all the way to the end because you need some metal to turn into the magnet. Instead, when you want to start again, run the wire straight back to the top and start wrapping again in the same direction.
And keep wrapping and wrapping until you get to this. Now, I've used some electrical tape here, here, and here to hold it all together.
Using your wire strippers or a craft knife and the help of an adult, remove the plastic coating from the ends of the wires. Attach these wires to the wires from the on-off switch with electrical tape, or attach them directly to a battery if you don't have an on-off switch. And ta-da, you have an electromagnet with your on-off switch. All you need to do is take the things you're going to magnetize, turn your electromagnet on, and suddenly it becomes a magnet. Pretty amazing, ha 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 ha. And then you can magnetize to your heart's content. But when you're done, don't forget, you want to turn it off. So that's what we're gonna do today on Science Max, Experiments at Large. We're gonna max out the electromagnet. So, where's my lab coat? Oh, there it is. We're gonna see how big we can make an electromagnet. And when I say we, I mean me and an expert. Let's see. Oh, Heather from the Ontario Science Center. She knows her way around magnets. So let's see. Yeah. I wonder if she's busy. Well, let's find out. And after we're done, I'll need to come back and clean up the giant mess I made in the lab. Hi, Heather, how you doing?
Good to see you, Phil.
I was just wondering if you could help me with something. Are you busy?
No, I got time.
Okay, great, because I'm gonna make a giant electromagnet experiment and I need your help.
That sounds like a lot of fun.
Okay, great. Let's go back to Science Max headquarters.
Oh, via the portal?
Yeah, by the portal.
Oh, okay.
You sure? I
Yeah.
know you're hesitant, so I want to reassure you, nothing will go wrong.
Great, okay.
Okay. Oh, hey, we're here.
It's
okay, it's okay. Don't worry about it.
No,
I
think definitely.
It's fine.
You all right?
Yeah, I was supposed to come in over there, but I came in over here. Oh well. So today, Heather, I want to max out the electromagnet. Turn it on, and it's a magnet.
Pretty good.
And turn it off, and it stops being a magnet. I want to make this into a much bigger, maxed out version.
All right.
So what are some of the things we can do to do that?
Well, actually, if you have a larger battery, one that has a higher voltage, we can try that for sure.
Okay,
that
so
will help.
there are batteries that are 12 volts?
Yes.
We could try one of those?
Give it a try,
I think
for
those
sure.
are like bigger, right?
Yeah, bigger, more powerful, absolutely. Now, that's one thing you could do. You can also increase the number of wraps of our coil here.
So how many times we wrap that wire?
Yes, we'll increase that magnetic field, making our magnet stronger.
And of course the nail, which is important because that's the thing that eventually becomes the magnet, right?
Right on, yes.
So what I thought we would do is we would start with a bigger nail.
Oh.
What, right? So larger battery,
Yes.
more voltage, and a lot more wraps of the wire.
Right on, and we have more space for that now, which is smart. Good job.
Great, okay, so we'll get to work.
Great.
Max Historica.
If you've ever seen a compass, you know that the needle points north. That's because a compass needle is a magnet, and it points towards the Earth's magnetic North Pole. And I'm using this compass to try to get to the North Pole. But it isn't easy. In fact, scientists knew there was such a thing as the North Pole as far back as the 16th century, but no one was able to actually get there on foot until 1927. You'd think it wouldn't be that hard, right? I mean, the needle points you straight there. Just follow the needle, right? But now that I'm here, I realize it's really difficult. I mean, the wind is incredible and the snow is intense and it's so cold. My hands, yeah. So, okay, we're not really at the North Pole. We were just sort of recreating that. But still, I salute the brave explorers who tried to make it there in the name of science. And I got a sense of it because the wind from the fan and the fake snow was. Okay, everybody, let's pack it up. I mean, that was pretty good. I just didn't know about that other camera.
So, back to our main experiment, where Heather and I are building a larger electromagnet. An electromagnet works like this. When an electric current is traveling through a wire, it creates a magnetic field. If you wrap that wire around something ferromagnetic, that's something made out of a metal that is attracted to magnets, like an iron nail, then it becomes a magnet. You can make a magnet stronger by wrapping more wire, which gives more distance for the current to travel, increasing the magnetic field, and you can also increase the strength of the current. Heather and I start with a coil of 30 meters of wire and start wrapping. And wrapping. And wrapping.
There, the wire is now all done. And remember, if you're doing this at home, do not use a drill unless you have an adult to help you out, because drills can be very dangerous. This one goes at a very slow speed, so it was okay. But yes, definitely an adult supervised activity.
Then we attach another on-off switch and make some leads that connect to a 12-volt battery. So, more wraps of wire and more current means the electromagnet should be stronger.
Okay, so we're gonna try this electromagnet, and we're gonna pick up this stuff right here.
Great.
Ready?
You ready?
Yeah.
3,
2, 1, go! Is it on?
Yeah.
Wow, it really does, you can't tell that it's on, but...
No, but bring it closer and...
Oh yeah, look at that. Okay, let me turn it off.
All right.
Let's see if this nail can pick up this nail.
All right.
Ready?
Ready?
Go. Oh. Okay, how about this side? Oh, no. No.
I don't think we're strong enough.
It's not strong enough. I think that we need to max this out even more.
Even more?
Right.
So I'm thinking there are a lot of appliances that use electromagnets, meaning it's already set up, it already has tightly wound coils and high voltage. So we're in a lab here. Maybe do you have old appliances around?
I have parts bins with a whole bunch of stuff. Maybe we could find some electromagnets in those.
Let's do it.
Okay, great. Let's go. All right. Pliers, battery, copper wire. Now, if you've already done the electromagnet experiment, here's another experiment that uses all the same materials plus these. Ha! Neodymium magnets, some of the strongest magnets you can get. So, here's what you need.
A battery, some neodymium magnets the same diameter as your battery, copper wire, and some pliers.
So here's what you do. First thing is you put the batteries and the magnets together, like that. Then what you want to do is bend the wire so it's touching the top of the battery and goes around the battery and then touches the magnets at the bottom. Here's what that might look like. I say might because you can do any shape you want. I've made a coil here, and if you put it over the battery, you'll see it only touches the very top of the battery and the magnets at the bottom. And if I let it go, it spins. It's a homopolar motor. What happens is the battery sends an electric current through the copper wire, and that turns it into an electromagnet, which is attracted to the magnets at the bottom, and it spins. So, now, let's max it out. Aha! A D-cell battery, which is larger and, of course, larger neodymium magnets. And you do the same thing. Make a coil that only touches the battery at the top and at the magnet, and ha-ha! It spins! Maxed out homopolar motor. But don't worry, this is not the biggest size we're gonna do. Come on. Maxed out homopolar motor. I have 27 D-cell batteries, a giant copper tube, and a neodymium magnet. So I'm just gonna, and then we get rid of that. Put this down. Okay, so the first thing I do is attach the neodymium magnet to the batteries. And I've got all the batteries taped together here so they'll sort of stand up like this. Huh? Giant stack of D-cell batteries. Okay, now what I do is I take the copper coil. I take the copper coil. I need to get. Okay, hold on. I got this. I just need to get the copper coil there. I did it. Okay, so I take the copper and I put it on top of the D-cell batteries like this, and then I let it go. Let it go. Nope, whoa. Homopolar motor. Okay, so that didn't work. But that's okay. I like it when it doesn't work, because that's science. It's not science if it works perfectly every time. I mean, you gotta have some room for improvement.
Heather and I built a larger electromagnet, but it still wasn't as powerful as we hoped. So now we're searching for parts that came out of an appliance that are pre-built electromagnets.
What about this?
I think that'll do the trick.
Do you think that does look like an electromagnet, huh?
It does, yeah.
And there's a whole big bunch of copper wires coiled on
Coiled
that.
around.
So you think we can use this?
Yeah, let's try it.
Okay, great.
We built the next version of the electromagnet. This one already has the copper coils, so it's just a matter of attaching wires and an on-off switch, and attaching all of it to a 12-volt battery.
Do you think 12 volts will be enough?
Let's find out. I think so.
Try that.
Once we do, it works much better.
Oh, no problem at all.
Ready?
Yep, turn it on.
On.
Whoa, pretty good. Okay, off.
Off.
Neat. In case it was really strong, I have the next step. Horseshoe. Okay, ready? Oh, whoa, that's,
Here.
I can't pull that off. Okay, wait, grab this. Okay,
Work together.
yep. So that's passed all of our tests.
Yeah.
This is really strong.
Is there
What
a
do
way
we...
to test it further?
In order to test how strong our magnet is, it's as easy as seeing how much weight it'll lift. Heather and I find a metal table.
All right, Phil, so I brought the electromagnet.
Okay.
Just put it right here.
Yep. We add some sandbags for more weight and then attach a scale so we can measure how much weight we're lifting. We use a chain hoist, a simple machine made for lifting heavy things. This one can hold up to 454 kilograms.
Want to turn it on?
We're ready?
Yep.
Here we go.
You can read on the scale how much weight is being lifted.
And that scale is going up.
Pounds on this side, kilograms on this side. We keep lifting until...
Oh, okay, so how much did it hold?
It held 100 kilograms.
Oh, that's more than I weigh, which gives me an idea. Come on.
This is ferrofluid. It is ferromagnetic, which means it's attracted to magnets. And I know what you're thinking. You're thinking, it's not that interesting. Well, watch as I put it next to this magnet. Very interesting. And because it's a liquid, it behaves in very interesting ways. Watch this.
Unlike most things ferromagnetic, like paper clips or iron filings, ferrofluid is a liquid, which means it behaves in a unique way. The spikes it creates are following the magnetic field lines of the magnet. You can see the magnetic field in 3D. It's even more impressive when we max it out.
This is ferrofluid outside of a glass jar. Now, it's sitting in a pool around this electromagnet. And this is a dial which I can use to change the voltage of the electromagnet, making the magnet stronger. Watch this.
Changing the current going to the spiral in the middle turns it into a magnet. The more current I put in, the stronger that magnet becomes, allowing the ferrofluid to climb the spiral to the top.
And remember, even though it looks all spiky, it's still a liquid. I will demonstrate with my plastic spoon. And watch this. When I turn the magnet off, it stops being spiky. Turn it on. Turn it off. Science.
The Wizard Academy. All you have to do is demonstrate true magic. And you will be granted entry. Well, Fuzzix, who is the next applicant for the Wizard Academy?
Overwhelmo.
Indeed, it is I, Overwhelmo. And prepare to be overwhelmed. Would you be flabbergastified if I balanced this coin on its end?
Not really, no.
But
Would you be impressed if I was to balance this coin on top of this coin?
Possibly.
Prepare to be flustered and stupefied. Stupeflustered as I balance 3 coins on their ends on top of this glass.
Well, that certainly would seem like magic. Let us see.
Okay. No pressure, Overwhelmo. You can do this.
And now, I say, a magic word. A magic word!
Ha 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 ha! And now you must let me into your academy.
Wait. What's under the cloth?
What cloth? This cloth? Nothing. Oh,
Is that a magnet?
this? No.
The pull of the magnet is what's keeping those coins up. The magnet is just strong enough to keep the coins from falling.
No, this is set dressing. It's just.
It was a good trick, but it's science, not magic.
Well, yes. And you will see! You will see! I will be back! I, Overwhelmo, will return! And I will do such magic that you will need extra socks. Because I will knock them off! With my magic, you will need at least 2 pairs of socks, maybe 3 pairs of socks.
We can still see you.
No, you can't!
So back to our main experiment. Heather and I have created a very strong electromagnet that can hold a lot of weight,
It held 100 kilograms.
Oh. which gave me an idea.
All right, you ready?
Let's do it.
Electromagnets super maxed out experiment. We've got,
2 electromagnets, 1, 2.
and those are wired to 2 batteries, which are on my belt, just like this, so that I can carry them around. And we've got a crash mat here, because
We need to keep you safe because you're gonna be using these electromagnets to get across this massive beam above us.
that's right. I'm gonna stick to this metal beam and go across with the electromagnets.
Wow.
We hope.
I have faith.
I'm glad you do. I've got a helmet for safety, goggles for safety, gloves for safety, but in this case, sometimes the lab coat is more safe and sometimes it's less safe. This time, it will get all caught up, so no lab coat. All right, you ready to go?
I'm ready. Let's do it.
Okay.
Oh my goodness. What?
Okay.
Because each of our electromagnets can hold more than my whole body weight, I can use them to cross the beam. When they're on, they stick like, well, magnets. And when I turn them off, they stop being magnets and I can move them along as I go. Now, this is something you should definitely not try at home.
Come on, Phil. You're almost there.
We did it! Yeah! There you go, Science Max, experiments at large, electromagnets! You wanna go?
No,
You sure?
I'm positive.
Okay, I'm going again. Woohoo!
Crazy.